Hello, my name is Anish and I'm a member. I've been working on Openstack and Kubernetes integration alongside Dennis, Jesse, Yao, and Alex. Our mentor was Devanam Srinivas from Huawei. The motivating factors behind the project were twofold. The first one is that Kubernetes support for OpenStack has been lacking, especially given that OpenStack is a premier private cloud provider. It makes sense to sort of work on showcasing some of like the possible integrations and the power of Kubernetes with OpenStack. The other thing we're aiming to address is Kubernetes' lack of multi-tenant and single-tenant clusters. Though it has support for namespaces and role-based access control, it's very difficult to enforce single-tenant nodes in a multi-tenant cluster. As such, our goals are, well, firstly, to showcase some Kubernetes OpenStack integrations by utilizing Keystone to authenticate users. This leads into our second goal, as using this Keystone authentication will allow us to enforce single tenant as well as multi-tenant nodes by restricting the namespaces and nodes that users are able to deploy to. The users of our project are, well, firstly, IT departments, like administrators in these departments controlling large shared pools of resources, as well as labs wanting to deploy applications to this infrastructure. Again, this would be useful for both of them, as it's cheaper for departments to maintain shared resources and to sort of allocate them as and when a lab needs it, as instead of having dedicated resources available for everyone at all times. So in terms of authentication, our initial aim was to utilize a webhook. Kubernetes allows external authentication using webhooks. Whenever a Kubernetes user tries making an API request to the server will communicate with the webhook and attempt to authenticate the user's OpenStack credentials with the Keystone authentication endpoint. Once these credentials are verified or not verified, the webhook will communicate back to the Kubernetes API server and to determine what the user status is. What we ended up implementing was a slightly more basic approach. We're using a static password file. After manually authenticating a user's credentials through the Keystone API, we store these credentials in a basic auth file for the which is utilized by Kubernetes. Right, now we'll show you. Now we're showing a visualization of what the entire process looks like. The user has a token, username, and password which they provide to an administrator. The administrator passes these through a Python script to verify that they are correct credentials. If the Keystone API responds with a yes, these credentials are valid, the Python script writes them to a basic authentication file, which is utilized by the Kubernetes API server. Now, whenever a user attempts to run a kubectl such as kubectl get pods, the API server will ask them to log in if they aren't already logged in with a username and password. The API server will then check these credentials versus the basic authentication file that was generated previously. If the user's credentials match something that exists in this basic auth file, the server moves on to the next step, which is checking for authorization. The way to check for authorization is, again, it's through RBAC. So if the user has a role which contains the power to do whatever the user is attempting to do, Kubernetes will allow them to do it. Otherwise, it will stop them from doing anything. So that's the Keystone authentication. On the other hand, we also had to figure out how we wanted to schedule applications on a single tenant as well as multi-tenant basis. Our initial approach was writing a custom scheduler to completely replace the default Kubernetes scheduler. While the scheduler was able to deploy applications, on a hard single namespace per node basis, it wasn't very smart about allocating resources for pods or even determining where to place them beyond single namespace per tenant. We wanted to sort of fully utilize the power of like the default Kubernetes schedulers, especially given how much work has been done on it. So we ended up moving towards a different approach. The second thing we developed was using extenders. Kubernetes has support for scheduler extenders, which are basically for a way to force the Kubernetes scheduler to make an HTTP call to a so-called extender. These HTTP calls will take place after either the node filtering stage or the node prioritization stage. We were able to successfully implement a scheduler extender, which again was able to deploy on a single namespace per node basis or multi-tenant nodes. However, we found that while this worked, it does have a performance hit, and since we hadn't developed a very robust keystone authentication integration, there wasn't necessarily a need yet for using an extender. As such, we decided to see if we could implement really force single tenant and multi-tenant deployments just using the default Kubernetes scheduler flags. So for this, again, the idea behind using this is we are enforcing single tenancy and multi-tenancy by forcing users to log in before they actually deploy any application. So we know that a user can't deploy to a namespace if they don't already have access. It was made possible by using Kubernetes, node affinities, anti-affinities, taints, annotations, and labels. So in terms of visualizing what it looks like, say we have a cluster with 4 nodes and a master node. Nodes A and B, in this case, are single tenant and belonging or earmarked as belonging to namespaces 1 and 2, respectively. Nodes C and D are marked as multi-tenant, so applications can be deployed there without worry of what's going on. So the first application we want to deploy is a single tenant application belonging to namespace 1 with 2 pods. The second application we deployed is a single tenant application belonging to namespace 2 with 2 pods. The third application is multi-tenant and is a member of namespace 3 and with 4 pods. The fourth application is also multi-tenant, but belonging to namespace 1 in this case, and it contains 2 pods. As you can see, node C has 3 pods of namespace 3, and node D has the last remaining pod of the third deployment, as well as the 2 pods belonging to the fourth deployment. So now we're going to demonstrate the process for a cluster admin to create a new user, as well as what the experience would be like for a created user. The first thing we do is use Openstack to issue a new token for the user. We then have to export this token to an environment variable, which will be utilized later in a Python script. We also export a username and password. We exported the password beforehand since we didn't want to show it in the video. These credentials will be authenticated versus the underlying keystone infrastructure. The process for writing these credentials to keystone ahead of time on the MOC is fairly straightforward. You just follow a few instructions, so we're not covering that. So when we run this Python script, you can see that a new user is created and it does authenticate the token for that user. The next step is actually restarting the API server, as it doesn't pick up the newly created basic auth file, so we just have to manually force it to restart. This usually takes about 30 seconds. Okay, now that the Kubernetes API server has reset and it has access to the basic authentication file we created previously, we're going to start creating a user. The first thing we have to do is actually create a namespace for the user, so we're just sort of demonstrating that. It's simple. We have a YAML file configured for this creation. It's a basic kubectl command. Next step is creating a deployer role. This role will have the minimum amount of permissions required to deploy an application. You can have different types of roles. It's just the one that's relevant to us right now. After this, what we will do is set our context. Doing this lets us set our context to always use namespace, like the N1 namespace. It just makes things a little less repetitive, and that's just how Kubernetes does things. The next step is creating a role binding between the deployer role we created and the previously created username. We also have to specify the namespace for this role binding. Once this role binding is created, we create a second one, as you have to create a role binding for every role. We already created one with just sort of demonstrating that. The next thing we do is set our current context to using the N1 context for all our commands. Now we'll try deploying a few applications. So as you can see, we have four applications we can deploy in this folder. Two applications belong to the N1 namespace. One of them belongs to the N2 namespace, and one belongs to the N3 namespace. The applications with single in their name will be deployed on a single tenant node, whereas the multi-tenant nodes will have multi in their name. Our current user has access to namespaces 1 and 2. Now we create an N1. So since we're not logged in, it's going to ask us for our username and password. So as you can see, the application is deployed without issue. Now we're going to try deploying an N2 application. This was also successfully deployed, as we do have access to the N2 namespace. Now, our user was not created with N3 authorization. So when we attempt to deploy an application to N3, as you can see, we get a forbidden error since we don't have the right permissions for it. We're going to deploy another N1 application just to showcase our scheduling. Now we will change users. Or we'll use a different user to deploy these applications now. So this user, which we just attempted to use, does not have access to N1. So again, as you can see, it was rejected. See, this user had access to N3 and was able to successfully deploy an application. Now we'll sort of demonstrate how the applications are deployed. We switch context to admin. Yeah, and now we have a list of the nodes. So we have a list of our nodes. Now we're going to show all the pods that were deployed in the N1 namespace. As you can see, to the pods which were marked as single tenant nodes were both deployed to names node 1. Again, the N2 applications were supposed to be on a single tenant node. They've been deployed to node 2. And now for N3, we can see it's supposed to be a multi-tenant deployment, and you can see they're placed in node 4 and node 3 respectively. The N1 multi-deployment is also placed, funnily enough, in node 3 and node 4. So you can see we have both single tenant and multi-tenant nodes in the same cluster. So now that we've seen the demo, there are some limitations to our system. The first is that since we rely on default Kubernetes scheduler flags, it's all on the YAML files which are provided by the lab. So this requires admins to sort of keep an eye and verify all of these files to make sure that labs aren't deploying anything that they shouldn't be, which may cause issues with the cluster, both within their own applications or without. Another limitation or downside to our system is that credential information is stored on the master node, which, even though only admins have access to it's still not an ideal situation. They shouldn't be stored anywhere there. The third problem is that it's a very tedious and long process. Admin users have to do a lot of setup, and resetting the Kube API server can sometimes take quite a few minutes. So in terms of scalability, it's not very quick. So leading from the limitations, future work for our project, first is really developing the Keystone webhook integration. This would address both the needs of the manual nature of creating a new user for admins, as well as the storage of credentials on the master node. Keystone webhook would remove the problems faced with both. This also leads into the next point, which is smarter scheduling using the scheduler extender. If we were able to authenticate fully using Keystone, we'd be able to force pods to deploy to nodes, and we wouldn't be forced to police YAML files, which again reduces the load on admins, makes it, I think, easier for users as well, so everyone's happier. And again, third, our project's only aiming to sort of demonstrate an initial integration between Openstack, Keystone, and Kubernetes. There's a large number of other Openstack projects which need further work on, such as Cinder, Neutron, and Swift. We learned a lot as we worked on the project. Of course, by just the nature of our project, we learned about containers and container orchestration technologies such as Kubernetes and OpenShift. We naturally learned a lot about OpenStack Keystone, as well as using the MOC. We also developed knowledge regarding Ansible playbooks, because we were initially thinking of creating playbooks for quick installment of spinning up of new clusters, but we quickly discarded them as we had more important things to work on. We also found that agile software development is surprisingly hard. It sounds simple in theory, but there's always so much to do. It's difficult to draw a balance between debugging and working on new features, and I think we erred on the side of debugging too much. We also were surprised to find how helpful the open source community is, engaging, especially the Kubernetes community. We were able to fix a lot of our problems and develop a better product overall.